Hi everybody, this is Dan here and welcome to Wandering DMs. Paul is actually off wandering among the streets and avenues today, so slightly stripped down version of Wandering DM today. This is actually the first time that we've only had one person on it, namely myself. So a little different thing I figured I'd talk about today. Basic dice probability is what I figured I'd talk about. Some of you may know that I'm actually a college lecturer for my day job in math and statistics. So sort of one of the main things that I focus on is probability and statistics and data in gaming and how that informs game design procedures and stuff like that. So figured for starters, let me just give a talk maybe for people that are brand new to D&D or role-playing games about basic dice probability type stuff. And for those of you who are real old schoolers, you might very well know all of this already, but along the way there will be and I'll try to throw in a couple of questions that I'll try to make like might possibly stump a beginner at least, so you can kind of think about that. So along the way, I could get perfectly formal mathematically about this. I tend to try to skip that and just give some basic ideas. So I think if you brought another college professor into the room, they could probably pick on some things that I'm saying that aren't completely strictly true, but the language that I use, we could boil it down to math formalism and actually make it totally correct and totally rigorous and totally provable if we wanted to, but I'll just kind of try to keep things brief. I do have the chat up at the moment, so if you do have a question along the way, I would love to hear that and see whether what I'm saying is totally boring for you, or I need to slow down or something like that would be great. And maybe I can do more stuff like this in the future if it works okay. So first thing is start with a little philosophy actually. What is probability really telling us? And you can get into these philosophical debates about that. And historically, there's at least 4 different camps about it. The middle two there are the ones that mostly get used today, the frequentist and subjectivist camps. And so basically, the frequentist camp, which has probably had most of the probability math work done in it, looks at a probability like 60% or something like that, and says, what is this telling us? It's telling us that if we were to attempt this process many, many times, tens of thousands of times or millions of times, we would succeed 60% of the time over a long, long series of trials. That's the frequency of a long series, the frequentist camp. On the other hand, the subjectivist camp is saying probability is really talking about a human mental state, is that we are about 60% confident that any particular trial will succeed for us. And you can, of course, as a philosophy guy, I kind of want to dig into that more, but we'll just move on from that and say, admittedly, there's actually already debate about what probability is even telling us. So we got to keep that in mind as we kind of confront these questions. And in fact, what camp you turn into actually can turn into actually different math procedures and different results for probability or statistics. But we'll if we need to, we'll touch back on that. Okay, so the second thing that I think about when I'm talking about D&D or dice probability is, am I dealing with a discrete probability distribution, or am I dealing with a continuous probability distribution? And actually, as a math lecturer, like at a slightly higher scale, these two flavors of courses determine what type of course you're in all the time, actually. If you're in a calculus sequence, that's continuous style math or real analysis. I actually teach a class now for computer science majors called Discrete mathematics, which is in some sense a totally different kind of math. So the nice thing is that, dice in D&D, they're always discrete. And that's the easy type. So when I come and I spend my off hours working on D&D or role-playing games, it's actually a real relief. It's a real entertaining break that I can just think about discrete stuff with dice as opposed to continuous stuff. So discrete means that there's only a finite number of possibilities, among other things, right? So here's your standard D20, and there's not an infinite number of combinations on it. There's only 20. And as a result, you take your total 100% and you divide it by, in this case, the 20 possibilities. Every single possibility has a particular positive probability of it actually happening. So if I take a D20 and I add 20 possibilities, obviously, and I ask, what's the chance of rolling a, you know what, I'll call out my good friends at the second best gaming stream, who their logo is the 19. So what's the probability of rolling a 19? Well, it's 1 out of 20, 1/20th, or 100% divided by 20 is 5%. So an actual, where is the 19? There it is. You see that? Okay, so thank you, second best people. Always entertaining. So what's the chance of rolling a 19? An actual particular percent, namely 5%, 1/20th. Discrete probability, it's kind of nice. Now, on the other hand, continuous probability would be what happens if you have an infinite number of possibilities. Like if you took the section of the real number line between 0 and 1, right, real numbers, how many points are there between 0 and 1? There's an uncountable infinity of them. So if you threw a dart randomly at that part of the real number line, what's the chance of landing on, I don't know, 0.19? What's the chance of landing on 0.19? Well, that's one chance out of infinity. And it really feels like, just on an intuitive basis, that 1 divided by infinity really ought to be 0, right? So there's actually, in a continuous situation, there's actually an infinite number of possibilities and a 0% chance that you land on any particular one of the infinite possibilities. That's a lot more complicated. Now, again, that's just kind of intuition. There's a branch of math called measure theory that makes that formal and rigorous and provable and all that kind of stuff. But that's basically the idea. So that's a lot more complicated, and you can't actually talk about any probability on any particular possibility in a continuous situation. That actually is a situation that you're effectively in when you're doing physics or something like that. So the best, in that case, the best you can say is, well, what's the probability of landing somewhere between 0.19 and 0.8? And for that, technically, you need integral calculus. That's a lot more complicated. So fortunately, we don't have to deal with that when we're dealing with standard role-playing game dice. It's always discrete. A lot of that stuff you can do in your head. And on my time off, it's actually a great relief. It's kind of a vacation from stuff where you absolutely need integral calculus to deal with. So yay, discrete probabilities. hope that made sense. Okay, so here's a question that a coworker once asked at, I guess this was my second computer game job, actually. So we're working on a game like Magic the Gathering. It's called Cron X at the time. Was that it? I think it was Cron X, and then I guess we were working on a couple other games after that, but kind of like a computerized Magic the Gathering at the time. And so my coworker asked this question here, thinking about dice and random type stuff. Question 1, can we talk about the average of a dice roll? And I kind of like this question because it says that, that my coworker was kind of thinking about the philosophy of what probability really means. When you roll a die a particular time, you only get one result, any particular time you roll it. On the other hand, I guess there's a lot of different possibilities. So can you actually talk about the average of a particular dice roll when you only get one thing each time you roll it? So if you're watching this later on, maybe pause the podcast or whatever you're listening to, and think about that. What would your initial stab at an answer be to that? Can we talk about the average of a dice roll? Okay, so the answer is basically yes. Now, technically, the correct term for that should be expected value, is what we'd really say. Now, fortunately for dice, the expected value, the average value you get, actually is just the average of all the faces, all the possibilities on a die. So I think I have an image for that. Yeah, okay, so expected values, like for a D6, right? You could just add up all the numbers, 1, 2, 3, 4, 5, 6, divide by the 6 possibilities you've got there. And as you can see on the screen there, that ultimately turns into 3.5, and that is the average of all the faces. Now, fortunately, for standard dice that are numbered from 1 to whatever, there's a shortcut that you can use. There's a mental shortcut you can use is where you can just add up. Since they're symmetric, fortunately, a shorter way of doing that is just add 1 and the highest number. So for a d6, 1 and 6, add that up, you get 7. Divide by 2, you get 3.5. So for dice, it's even easier than technically adding up all the possibilities, which is the definition. Or I suppose as I look at that, even easier than that, I'm going through the panel there, is you can take the highest number, divide by 2, and then just add 0.5 actually. So 6 divided by 2 is 3, add 0.5, 3.5, and there you pretty quickly mentally have the average result or the expected value from any particular die roll there. So kind of little shortcut that I use when I'm thinking about this in my head. So what is the expected value for a D4? Well, 4 divided by 2 is 2, add 0.5, you get 2.5, and so on and so forth, right? Okay, so there's all your standard dice expected values right there. They all end in 0.5 because of that, really adding 1 and whatever and dividing by 2. So standard result for a D8 is 4.5. There's your standard like AD&D hit dice values. You're all 4.5s on average. And your standard result from a D20 is of course 10.5. All right, so maybe you knew that. If you've been gaming for a while, that might possibly be obvious. But yeah, we routinely think about what's the average value of a particular die roll, particularly when you need to roll it a whole bunch of times. So so that's pretty easy. Now the next thing you want to think about, and as a little side point here, another thing that's kind of a relief when I'm dealing with D&D probabilities is everything that I ever do is basically like the first half of a Stats 101 course. We're not doing anything really crazy like inferential statistics with p-values or analysis of variance or anything really crazy like that. It's really all the first 6 weeks really of a Stats 101 course. So it's pretty basic stuff once you get introduced to it the first time. So averages, expected value, very, very simple for dice. And then the next question you want to ask yourself is what about the variation? What's the variance? So if you've heard that just a couple times or you're hazy on that, let me give you kind of just a brief idea of what that means. So variation is coming up with some way of measuring whether your dice rolling is likely to fall real close to the average or real far from the average. And again, technically I ought to be saying expected value there, but whatever, it's really the average. Okay, are you likely to fall close to the average with a particular number or fall far from the average on a particular die roll or series of dice rolls? So ways that you can measure this, is actually a whole bunch of ways you can measure this, right? There's calculations called variance, there's standard deviation, there's average absolute deviation, there's interquartile ranges. There's a whole bunch of ways you can measure this. Probably the most common one is standard deviation because it's kind of easy to interpret. Standard deviation, and there's a formula for it. We don't care about that right here. So standard deviation is kind of sort of the average, how far off you are from the expected value. Okay, so if the standard deviation is 2, then you're saying on average I'm around 2 more or 2 less than the expected value. Or you can say it's the average, how far I am from the average. Okay, it's actually kind of important because the different procedures will have the exact same expected value, the exact same average, and you want to have some way of numerically distinguishing between the different variations in your die rolls. I guess I should say, so like even like the average, there's different ways of calculating that, right? So in a Stats 101 course, they're going to tell you about the mean, the median, the mode, stuff like that. Now for dice, they're all the same, right? So for like a 1d6, I've been saying the expected value is 3.5. Well, that is the mean, and that's also the median, right? So all those different ways of calculating averages for dice, they're actually all the exact same thing. So that's why I didn't think to mention it earlier. All right, so okay, so here's a question. Having introduced variation just kind of briefly, which do you think has the greater variation? rolling 1d6 or rolling 2d6 and adding them together. Now, maybe this is a hint that might help you out. The expected value, and as you can see on the screen, the standard way of writing expected value is the function e with some kind of process inside it, some kind of random variable I'm supposed to call that. So the expected value of the 1d6 is 3.5, like we said before. The expected value of rolling 2d6 is 7, twice as much. Okay, so maybe if you have the opportunity, pause the video here and see what your instinct would be. This isn't enormously hard, but what would your instinct be for which has the greater variation, 1d6 or 2d6? Okay, so the answer is 2d6. Hopefully that was pretty obvious. So again, if variation is trying to measure how likely you are to be far away, we could pull out the standard deviation formula and we could compute it for those two things. But if you just kind of think about it intuitively, like how far away, for 1d6, how far away could you be from the average? Well, the highest thing you can possibly roll is 6, right? And 6 minus 3.5, that's 2.5 if I'm not hallucinating, right? So the most you could possibly be away from the expected value on 1d6 is 2.5. But on the other hand, with 2d6, you can roll up to 12 on that, right? And if the expected value is 7, that means you can be up to 5 pips higher, right? So the 1d6, you can only be 2.5 higher, but the 2d6, you can be up to 5 pips higher, twice as much as the 1d6. So that at least begins to suggest that the 2d6 has higher variation. You can be further away from that middle point than on the 1d6. So, and again, we could pull out any one of those formulas and confirm that, but that's the case. So in general, that tends to be true for even larger dice values. So you talk about 3d6 or 4d6, the more dice you're rolling and adding them up, the higher the variation is going to be, right? I mean, the higher the average is going to be, higher expected value, and also the higher the variance as well. So roll more dice, add them together of the same type. That's kind of important. And the variation will go up as well. There have been days when I actually got hazy on that fact. In the past, I've made a mistake at least once about that fact. But roll more dice and the variation as well as the expected value goes up. So that was question 2, right? So hopefully you're doing pretty well so far. Okay, so, right. Okay, so let's look at some charts, right? So to get a little bit more specific about the difference of rolling 1 die versus 2 dice, here are graphs of all the possibilities that could happen when you roll 1d6 and all the possibilities you could get when you roll 2d6. These charts have been taken from Torben Morgenson's Troll dice roller, and Mr. Mogensen has, I guess he works at the University of Copenhagen, and he has this delightful formal language actually for dice rolls, and he has a website where you can use that. And usually his Troll dice roller, or I guess that's short for Torben's roller, I think if I recall, is probably my go-to for like dice probability statistics and stuff, and it just instantly pops out pretty much anything you would want. I've actually rotated it 90 degrees, his chart's 90 degrees to be more like what we'd expect. So on the left, you have the results for 1d6, and you either get 1, 2, 3, 4, 5, or 6, and there's 1/6 chance. Again, this is discrete probability. So there's a 1/6 chance of getting 1, 1/6 chance of getting 2, 1/6 chance of getting 3, and equal probability for each of those possibilities. The graph there looks flat across the top, and the standard term for that is a uniform distribution. So really, really easy when you see that kind of chart. On the right, you have 2d6, and here you can get anything from between 2 and 12. And if you look at all the possibilities, there's one way to get a 2, namely you got to roll 1 and 1. There's 2 ways to roll a total of 3. You're either going to roll a 1-2 or a 2-1. There's 3 ways to roll a 4, and so on like that. 4 ways to roll a 5, 5 ways to get a 6, 6 ways to get a 7, and then it starts going down again for 8, 9, 10, 11, 12. And again, for 12, there's only one way to get it. You got to roll double boxcars. So the fact that each of those possibilities goes up by exactly 1 pip, 1 out of the 36 total possibilities, For what it's worth, the textbook that I use calls that 2d6, when you're adding two random variables, calls it a triangular distribution. And obviously there's more possibilities in the middle, and there's fewer possibilities out on the tails, on the ends. And some people would want to call that bell-shaped or a normal curve, and I would really have to disagree with that pretty strongly. Please, you really should not call that one of those other names. That's really a triangular distribution. If you take a ruler on the screen there and put it up along one of the two diagonal sides, you'll see it's a perfectly straight line. It really looks like a triangle. So I tend to be pretty careful about that for a 2d6 distribution. That's actually, I think, a common mistake that people want to call that by some other name. Let's look at a 3d6 distribution just to kind of continue in that direction there. So 3d6, obviously that's your standard original D&D ability score rolling. I guess like an AD&D, I think maybe like with a two-handed sword against a giant, that's what you roll for damage. So the possibilities there between 3 and 18, and the numbers get a little bit more complicated. But if you chart it out like this, I'm not going to call that triangular because it's not an exact line. This I would start to call, again, a little bit more humped up in the middle. It's got a little bit more curvy shape to it. This I would be willing to call at least kind of bell-shaped. Still don't want to call that a so-called normal distribution. We'll see that in a couple minutes. But I would at least call this a sort of kind of bell-shaped. It's got all the little jaggy things, a little step-by-step because it's still discrete. But this I would say, well, the best description I can think of is it's kind of bell-shaped for 3d6. And I suppose I could have thrown another question in here of like, what do you expect for 4d6? What do you expect for 5d6 or 6d6 for fireball dice? Do you think it would look more bell-shaped, or do you think it would look less bell-shaped than what we just saw? That's a common question. I actually don't talk dice in my college math classes, but basically I asked that question in class, and it's very, very simple. I would expect that to be more and more bell-shaped, more and more curved, more and more well-shaped like a bell. And that actually is what occurs. So that idea, mathematically formalized, is probably the single biggest idea that I feel that I actually understand in mathematics. And the name for that, and if you take Statistics 101, this ought to be one of the key ideas that shows up in that semester. So that idea is called the central limit theorem, or the CLT if you're talking about this a whole lot. So the more and more dice that you roll, the limit, that's what the word limit means, going in the direction of infinity, the more and more it gets piled up in the center of your graph, and the more and more that centralized graph looks like a smooth curve. Theorem means this is something we've actually proven. We've definitively proven, we can guarantee that this is the case all the time. If we take a random variable like dice rolling, and we decide we're going to be rolling them and adding them together, and we add more and more and more dice, 3 dice, 4 dice, 5 dice, 6 dice, and we keep doing this, the possible results get more and more bell-shaped the more you throw in there. Basically, that's my idea for the central limit theorem. Now, one of the important middle words there is the word adding. Any kind of process based on addition is going to work this way, and is going to give results more and more bell-shaped the more dice you throw in it. So that would be adding things, that could be averaging things, that could be taking proportions where you're basically just counting how many things you got and dividing by the total. Counting is basically just adding ones up. Any one of those kinds of processes that's really based on addition is going to fall into this central limit theorem situation and create more and more smoothly bell-shaped possibilities, with more of the possibilities all heaped up in the middle like that all the time. So that's actually, if you're talking about rolling batches of dice or fireball damage or something like that, or hit dice for really big creatures or monsters in D&D, it's really helpful to have an idea that the central limit theorem guarantees you're going to have that shape more and more the more dice that you're throwing into the mix. And the end result of that, right? So I could ask, well, what happens if you were to take 10,000 dice, if you were to take 1,000,000 dice, or go in the direction of infinity? So that is what really people mean by this phrase normal distribution, right? You kind of want to be careful about this, about using the phrase normal distribution, because as I saw another math person say at one point, the normal distribution is something very, very special. And that's the continuous limit of doing the CLT process over and over and over again with larger and larger amounts of dice towards infinity, right? In some general sense, you're thinking about what if I did that with an infinite number of dice, or at least went in that direction and normalized the results at every point so I could at least see some kind of graph about it. And so the normal distribution is this perfectly smooth curve. This perfectly smooth curve, it's heaped up in the middle, it trails off very, very smoothly. And as you go in the direction of infinity here, you gotta remember now you have an infinite number of points. That distribution there is a continuous distribution. It's not discrete. And so now you land back at that introduction where I said discrete versus continuous. The only reason I even said that in this video is to point out that the normal distribution is this continuous limit, this continuous distribution. What's the chance of landing on 0.6 in the normal distribution? Technically 0, right? There's an infinite number of possibilities there, and each individual possibility has probability 0. So if you're going to be talking normal distribution probabilities, now you're back to integral calculus and saying now I need to take a slice between 0.5 and 1.7. What's the overall area in there? That tells me the probability of landing in between. That's a lot more complicated, right? So that's actually not something that I ever directly deal with when I'm doing gaming statistics. I can't remember the last time that I actually dealt directly with the normal distribution. That actually really should not be a factor when you're thinking about gaming dice. So it's important to know that's the ultimate going towards infinity end result of the central limit theorem. But if you're talking gaming dice, you really probably shouldn't ever really be using the phrase normal distribution unless you're saying I'm rolling an infinite number of dice, and then that starts to become on the table. So something very, very specific. It's a continuous distribution. I can say if I roll a whole bunch of dice, the results are going to look bell-shaped. That's correct terminology, but I would not want to say that it's a normal curve, because that's actually something different. It's continuous. It's not even discrete. So kind of be careful about that. I think I saw, this is on my mind because I think like yesterday, someone in an online group said that, and it kind of confused me and other people that were, mathematically better trained, I guess, or at least more careful in our terminology. So fortunately, I'm actually glad that's something I don't have to deal with in my gaming, because then calculus is back on the table when you want to deal with that. So yeah, okay. So let's go back and look at variation of a particular couple of important dice distributions. So here's my question 3 for today, and I think this is actually my last major question. So if you had to generate numbers between 10 and 60, right, and this actually happens a lot in classic D&D material. So original D&D, advanced D&D first edition, second edition, BX, they tended to not actually tell you what dice to roll. There would be, there's a lot of places where they say generate a number between 10 and 60 for number of giant rats or whatever. And you had to figure out what kind of dice to roll for this. So if I need to generate numbers between 10 and 60, there's at least 2 different ways of doing it. I could take 10 6-sided dice and roll 10d6 and add them all up. Or I could roll 1d6 and just multiply the result of that by 10. Now notice that all the first order statistics of those dice rolling procedures are exactly the same. The minimum number you're going to roll is 10. The maximum you can get is 60. The average or expected value is 35, right? That's the mean, that's the median. So in all those first order statistics, they're completely identical. But my question here is, which one do you think has greater variation? 10d6 or 1d6 times 10? So again, consider, if you can, pausing the video and thinking, what is your instinct for that? Which has greater variation, rolling 10d6 or 1d6 times 10? Okay, so the answer is the 10d6 times 10 has greater variation. And that can possibly, so I don't know if that surprised you. That's actually something I don't get to ask my statistics classes, but like every semester I kind of wish I could to find out what the instinct is at that point. I think there's been a time in the past where I was thinking that the answer was reversed, and then I thought it through, and I was like, oh no, it's actually it's actually where you're just rolling one die and multiplying it by 10. And possibly you might think that the 10d6 has way more dice and therefore way more possibilities. So that might be possibly the manner in which that question might trick someone. But remember what variation really means. It's, are you likely to be far away, or are you more likely to be close to the central expected value of your distribution? And I guess I think I have a chart of this here. Right, so here's 10d6 on the left, right, the overall distribution of 10d6, and sure, there's a whole lot of different possibilities there, but remember the central limit theorem. If you roll a whole bunch of dice like that and add them all up, the possibilities are more and more stacked up in the center, right? In other words, if we crunch numbers on that, you're more likely to land near the center. The variation is going to be relatively low for that. Now on the right-hand side of the screen there, I have the 1d6 times 10. There's only 6 possibilities. You're either going to get 10, there's 1/6 chance for that, or you're going to get 20, or 30, or 40, or 50, or 60. So whereas for the 10d6, there's practically no visible chance that you're actually going to get the minimum value of 10. But for the distribution on the right there is actually a 1/6 chance you're either going to roll a 10 or a 60 and be as far away from the center as humanly possible. So if you crunch numbers on that, the chance of landing far away from the center is much more likely, and that's going to be represented by a much higher variation score, whichever number you choose to crunch for that. But anyway, the short story is it's a lot easier to be far away with the 1d6 times 10. It's with the 10d6, you're almost guaranteed to be very close to the central value of 35 in this case. So I think that's the trickiest question that I was gonna throw out today. So feel free to send a comment about whether that was obvious to you or whether you were surprised by that. So among the ways that this shows up in discussions of D&D, like I've seen that material become a key discussion point at least twice recently in the Facebook AD&D first edition group. And one way that came up is in original or first or second edition, you make a random group of men, bandits, or this actually could be orcs or kobolds or something like that. So a random group of bandits, and the book says bandits show up in the wilderness in a number from 30 to 300. It just says 30-300. Doesn't tell you what dice to use. And then it says if you have more than 100, you get a captain. And if you're more than 200, you get 2 captains, and there's a chance for a wizard or a high-level cleric. And if you get 300, then you automatically have a high-level wizard or cleric. And someone said, have you looked at the chance of actually getting a number above 200? It's practically impossible when you're rolling 30d10. And he was right. That's a true statement, actually. If you roll 30d10, the central limit theorem hammers you, and practically all of your probability is all stacked up in this really narrow spike right around the average value of 175. Is that right? 330 divided by 2, 165? 165. So the chance of getting anywhere further away from 165, it's almost impossible to even get up to 200. But obviously that doesn't make sense. This rule isn't going to be in the book and then have it be probabilistically impossible to ever get a wizard or cleric. Why would you bother to say that? So the mistake he was making is that the intent wasn't to roll 30d10. The intent was to roll 3d10 and multiply that by 10. And then you get, a picture that looks a lot like 3d6. It's pretty likely you'll be in the middle. But there's a significant chance you land out on the highest or lowest possibilities. You can be below 100, you can be above 200, and all those possibilities for sergeants or wizards or clerics do come into play. So a lot of the numbers in classic D&D, where you're rolling 30 to 300 or 40 to 400, clearly, the intention there was roll 3 or 4 or 5 dice and then multiply it by 10 to get that last 0. If you look at a particular place in the Monster Manual 2 from first edition, there's actually a table that says, hey, you know, all those ranges we put in all the books so far, here's the dice that you're supposed to use. And actually for the numbers like 10 to 100, it actually explicitly says that, but you kind of have to know where to look for that. Second thing that came up recently, and this was just last night actually, was a gentleman was saying in first edition D&D, first edition advanced D&D, a lot of your weapons roll just 1 die for damage. I mean, I think many of us are familiar with that from original D&D or BX or 5th edition. I think works like that in almost all cases. Most of the time you're rolling 1 die, but in first edition there were some cases like a spear versus a giant or a 2-handed sword versus a rhino or something like that, whereby you might be rolling 2 or 3 dice, 2d6 or 3d6 or 2d8 or something like that. And the gentleman who pointed that out said, I actually don't like those 2 or 3 dice because, and then here's some language that wasn't exactly correct to begin with, because it's a normal distribution. And then we were confused and we were like, well, it's not even, I wouldn't even call 2d6 bell-shaped. Technically that's triangular. Okay, but it is humped up more near the middle possibility. And he was saying he actually didn't like that because it becomes somewhat more predictable what the damage is going to be close to the central value. And he's right about that. He said, I prefer a more uniform distribution because it kind of represents the unexpected high variance of combat, of lethal combat that I would expect. My take, once we hammered out the language, my take would be, my understanding of physics actually is it probably should be bell-shaped, actually. But for me, the gameability always wins, and I'm actually very happy to have a single die, very simple to roll, very easy to read and report. Uniform distributions are easy to analyze. So even if physically I don't think that's probably totally accurate for game purposes, I'm perfectly happy to just have 1 die. And that's one of the reasons why I'm really, really happy to play something like BX or original D&D, where you ignore the large target damage results, which I don't think you need to deal with, and just have 1 die per weapon. Perfect. I love it. But kind of an interesting debate about what would physically be more accurate, bell-shaped or at least triangular, or uniform distributions. Anyway, for me, that's one where maybe the realism goes in one direction and the playability goes in the other direction. And for me, in that kind of split, the playability always wins and the pacing at the table always wins. So I actually like the single die linear damage for that purpose. But you could possibly swing in another direction about that and say I prefer something more complicated. And there's been a whole lot of options in like Dragon magazines over the years, and a friend this morning pointed out that, so I guess in Dragon number 94, thank you, Landon, in Dragon number 94 there's a system that recommends divisions where you roll 1 big die like a d20 and you roll 1 little die like a d6 and then you divide them. And so so that'll turn into a right skewed distribution where most of the time the results are going to be 1 or 2 or 3. And once in a great while, this will be 20 and this will be 1, and the result will come out to be 20. Kabam! And it's actually the author who wrote that was like, this might be better than like your standard critical hits mechanic, whereby there's kind of a smooth gradation from normal stuff to crazy enormous stuff. And just for a second, I was like, yeah, that's a good argument, but man, I will get run out of town with pitchforks and torches if I ask for standard division damage mechanics. So I would not want to go in that direction very quickly. Okay, so I guess that was more or less my my basic dice probability presentation. So many of us are starting school up for the fall semester, either last week or this coming week or something like that. So I thank everybody for giving me the opportunity to kind of flex my lecturing muscles before I go back to school. So if you have comments or additional questions about dice mechanics, I would love to hear. I would love to hear that. If there was some kind of gap in what I was talking about, we would love to see that in the comments on YouTube. And Paul should be back next week for the full Wandering DMs experience when he comes back from his outing this weekend. He's been very busy for Wandering DMs and other stuff. So if among other things, you ought to be following Paul's blog, because his gaming last week was extravagant and was exciting for many of us to even read that. And if you don't like this topic on Wandering DMs, tell us so I can avoid it in the future. And if you do like this kind of stuff, please tell us, and maybe me and Paul can work in some more statistics, probability, nitty-gritty stuff, and we'd be happy to talk about that. Remember that you can now follow us on a whole bunch of social media. So on YouTube and Twitter and Twitch, all those services, we are Wandering DMs, and we check that pretty regularly. We also have personal accounts on Twitter and Twitch. And we also have a website as of a couple weeks ago, wanderingdms.com. And if you didn't already know it, wanderingdms.com, you can download audio versions of all of our streaming shows to date. Again, Paul's been putting that together, and it's a really wonderful resource for those of us like me, take mass transit to our workplace, for me to school, and we can very easily now get an audio version of of our shows and listen to it en route. And we also have a Patreon too. So on Patreon, look for Wandering DMs, and any little bit that you can give helps us make the shows, support it. We're engaged in improving equipment and the production values of our shows, so we're looking forward and excited to do that. And if you want to participate and help us out, we would really appreciate and love for you to be part of Wandering DMs in that way. So remember, we are live every Sunday at 1 p.m. Eastern Time. So do please come back in 1 week to see me and Paul and your comments, and for you to join us in another thought-provoking discussion. And we'll talk to you next time.